Hi, everyone, and welcome back to the third session of Oblivious computation, where Gilad is going to give the next talk. Gilad, please.
Thank you. Okay, so we are going to talk now about optimal construction. So just a recap. We have a secure processor, untrusted memory, and even though the information is encrypted, where I'm accessing reveal sensitive information. For instance, if I'm uploading genomic information of a patient to the cloud, and I always access the same places, then the cloud provider can infer that the patient has some kidney problem and not, say, a heart problem. And Oblivious compiler comes to make those access pattern to hide the access pattern. So we spoke about the lower bound, we spoke about tree-based ORAM yesterday. We also mentioned in the last talk the problem of Oblivious sort and Oblivious compaction, and we showed, and what we're going to talk now is about the hierarchical paradigm for obtaining ORAM, and in particular we'll go to the log-n construction. Okay, so there exists an ORAM with order log-n overhead amortized, and then we're going to make it also worst case. It's asymptotically optimal. It matches the two lower bounds that we have. It achieves computational security and matches Larson and Nielsen. And if you replace the PRF with random oracle, you're actually going to achieve statistical security. And the lower bound of Goldach-Ostrovsky also holds if the client has a random oracle. So we're going to match also Goldach-Ostrovsky in this model when it's replaced with random oracle. The setting is that the word size of the machine is log n, where n is the size of the memory, so each word is of size log n. So this is the classical model. Client's memory size is order 1 words. The server is passive, it doesn't like compute or do anything, it's just like a memory. It's on the balls and beans model, namely we are not going to use some encoding or bit slicing techniques on the data itself. There is very large hidden constant in this construction. It comes from the compaction that we saw in the previous talk. And it's based on the hierarchical ORAM paradigm that goes back to Goldach-Ostrovsky. Okay, so what I'm going to show now is a short tutorial of the progression in the hierarchical ORAM. We're starting with the very beginning hierarchical solutions, and then sees the really nice breakthrough of Panorama, but Patel, Persiano, Rakova, and Yeo, that came very, very close to the lower bound. The construction achieves log-n, log-n, and then I'm going to describe how to shave this additional log-n using in Optoram. Okay, so the hierarchical ORAM, the hierarchical paradigm. Goldach-Ostrovsky showed essentially how you can get a primitive, from a primitive that's called non-recurrent hash table, how do you can construct an ORAM. What is a non-recurrent hash table? So it's an hash table, namely, I need to have a primitive, an algorithm that supports two operations. First, I have a build. I get some array in the memory. The array contains pairs of addresses and values. And we have to build that, we have to, do some pre-processing, arrange the information in the memory. This is the build operation. Of course, it has to be oblivious. And then later, I'm going to get queries of the form of a lookup, where I'm going to get an address. And then if the address is actually in the array that was there in initial time, I'm going to return its associated value, and otherwise I'm going to turn a bot. In addition, I also might get lookup of an element that doesn't exist in X, or I'm going to get also dummy lookups, which are just pretend that you look up, okay? And what I have to do is to go to some place in the memory and pretend like I'm looking up without revealing what kind of query I receive. If it's a real lookup, dummy lookup, or an element that exists or doesn't exist, okay? And security, this is going to be non-recurrent. The only guarantee that I'm going to have is that each address is going to be searched and looked up only once. Okay, I'm not going to look up for the same address twice. And overall, I need to support not so many lookups. It's going to be proportional to the size of X. Okay, after I reach that limit, this construction is going to be destroyed. We're going to rebuild it again. So the idea of this construction is let's do balls into bins. We're going to take our elements, and each element we're going to mark on each ball, on each bin, we're going to put that ball. And then using Oblivious sorts, we can actually route the elements into the bins obliviously without revealing any information. And we need to pad each bin to its maximal capacity. Thus, we're going to have some dummy balls also introduced along the process. Let's see how to actually do it. So the size of each bin is going to be something like polylog in n. Let's say it's log squared n. And so the number of bins is going to be 2n over log squared. Okay, so this is what is called bin packing. I'm going to take my input array. On each one of the inputs, according to the key, according to the address, I'm going to compute a PRF. I'm going to have a PRF key, and I'm going to assign to each one of the balls a destination bin. I'm going to add a lot of dummy balls also. So I'm going to add to each bin exactly its capacity as dummy balls. And I'm going to assign the first, those balls to the first bin, those to the second bin, and so on. And given all this information, I'm now going to Oblivious sort. Now we're going to have collisions. So if we have all the balls that want to go to the first bin are going to be one next to each other in the memory. So you need to think of the memory as looking like that, okay? So all those, on this one I wrote 1 according to PRF, and all those balls I also wrote 1. And whenever I compare in the Oblivious sort, I'm going to prefer a real ball over a dummy ball. So the result is going to look something as follows. So I'm going to get all those that are 1, that are written 1, those are 2, those are 3, and so on. Now, what we're going to do, we're going to scan all those bins, and we're going to see all the elements that are overflows. And we're going to mark them as overflows. Okay, we can do that quite easily, just a linear scan. And then with one more Oblivious sort, we can remove all those elements that overflowed to the very end, and I got all my elements into the bins. Okay? Now, what's the idea? It's the idea that now I can do lookup very easily. When I need to look up for a ball, a specific ball, I'm going just to visit the bin that it resides. I'm going to compute it according to the PRF, and I'm going to scan that bin. And when I need to look up for dummy, I'm just going to visit a random bin and scan that random bin. Now, security is guaranteed because my promise is that I'm never going to query the same address more than once. Okay? I'm going to query everything at most once. And so it's really easy to simulate build, just Oblivious sort. It's Oblivious algorithm. It has a simulator. And simulating a lookup is just, it doesn't matter if you are looking for a real element, for a dummy element, or an element that exists or doesn't exist. I'm just going to look up for a random bin and scan a random bin. So the cost of build is n log n, and each lookup I'm going to scan the bin. It's going to be log squared. Okay, questions so far?
No questions.
Okay, good. So now given this hash table, we're going to build a neuron. And the neuron is just going to be a hierarchy of those hash tables. So we're going to have hash tables of different sizes, of doubling sizes. So we're going to have log n tables. The first table is going to be of size 1, and then the second one is size 2, and so on. And access to the ORM looks as follows. Each access has, read or write, address, and if it's right, we also have some associated data where we want to update the ORM. So lookup is going to be as follows. We're going to look up for the address in each one of the tables. If the item found in some table, we're going to pretend to look up in the remaining tables. Okay, so this is why we need lookup of dummies. Then after we found the element, if the operation is read, we're just going to retrieve that element. If it's right, we're going to ignore the found element and use the data that we found that we have to write. Okay? After we did those, we have to rebuild. So what do I do in rebuild? So some of the tables are actually built, some are not. And when I'm coming to write back to ORM, I'm going to look for the first empty level, and I'm going to rebuild that level from all the previous levels, plus the new element that just I found, I'm going to write it back. Okay, so after this operation, all those are going to be marked empty, and this one is full. When I going to write next, T0 is going to be full, and so on. Okay, so let's just look how run some examples. So let's say that this is my ORM. This is an address. This is the associated data on that address. Now let's assume that the client wants to read the content of 9, of address 9. So the way it's going to be performed is that I'm going to look up for 9 in the first one. Those levels are empty, I'm not going to access. Now I'm going to look up for 9 over here. Again, it's not going to be found. And only in this level, I'm going to find 9, and I'm going to see that it's BCD. Now I want to write it back, and cannot write it back. So I'm going to write it back to the first level. Now let's assume that the client wants to write the address 25 to the value GRY, okay, with the associated value GRY. So I'm going to access each one of the non-empty tables again. I'm going to look up for 25 over here, look up for 25 here, and here I'm going to find 25, and I'm going to mark it as consumed, and I want to run, and then I'm going to do dummy lookups in the remaining tables, and going to write back lookup on this one. However, this is full, I cannot do it, so I'm going to rebuild level T1 from the new element and from T0. Okay, after some more accesses, this one is going to be full, and then I will have to write to build this one from, I'm going to write this level and so on. Okay, so what is the cost of this, whatever I showed over here? It's a basic hierarchical ORM. So we are performing lookup. How much lookup cost? So recall that each access has some lookups, a lookup in each one of the levels, and then there is some maintenance of rebuilding a table from the previous tables. So the lookup operation, I'm going to have log n lookups on different tables, and each one requires roughly log square n according to the solution I showed. So it means that overall I need log cube n cost for just performing the lookup. The rebuild is, let's say I have only n accesses. Actually, I'm going to have much more, usually. So when I come to rebuild level I, I'm going to rebuild level I every 2 to the I accesses. So over the course of n accesses, I'm going to rebuild level I n over 2 to the I times. Each rebuild is an oblivious sort. It costs me 2 to the I times log 2 to the I. It's n log n. Okay? So overall, the cost over n accesses of rebuilding is this cost. I can take n over there, the 2 to the I cancels out, log 2 to the I is just I get overall n log square n, and this is over the course of n accesses, which means that per access, the cost of rebuild is something like log square. Okay? Throughout the years, okay, so what I just presented is an ORAM that cost overall log to the log cube. Over the years, there was improvement in the lookup, and essentially, we can, using also secondary hash tables in each one of the bins, or actually having better hash tables in each one of the levels, we can effectively search inside each table while paying only a constant term, plus we need some global stash to the entire structure. So it's effectively order 1 for each one of the levels, plus some log n for searching in all the levels. Anyway, it's the entire time for lookup costs something like order log n. And the rebuild stays log square n, where this extra log n comes from the fact that we do this oblivious sort that costs us n log. And then came Panorama, and with a very beautiful idea. And they say that if you remember our oblivious, the very first oblivious sort that I presented today, we say that if I first shuffle the inputs and then I can run something which is non-oblivious, it remains oblivious. So they came up with essentially the same paradigm, and they say that hash table, if I first randomly shuffle all my inputs to the hash table to come to build the hash table, then I can do it much faster. I don't need to pay n log n. I don't need to do it with oblivious sort. We can do it actually with just n log n. Cool. This already removes, shaves a lot in the build process, and we go down to n log n. However, our problem that it's not really randomly shuffled, like our input is not randomly shuffled. But they said they had the following observation that all the elements that we didn't visit, so when we come to a table, we rebuild the table all the time, right? Okay, we rebuild this table from those elements. We maybe not visit any one of those elements when we in the lifetime of that table. So they observe that if we didn't visit an element, then in the eye of the adversary, it still has no clue what is in those hash table, what it has in those tables. Okay, where each element resides. Only after I actually access something and I consumed it, it knows something about where the element was residing. Okay, so the idea is that all the elements that we didn't visit are still randomly shuffled in the eye of the adversary. However, when we come to rebuild the level, we don't just take it the previous level. We have many levels that we need somehow to merge into the new level that we are building. So even though each one of them might be shuffled, it doesn't mean that the concatenation of all of them is also randomly shuffled. So what they showed also how to intersperse two arrays in a procedure that costs roughly the size of the two arrays. Okay? So what it means that if I take in two randomly shuffled arrays, I can intersperse them together very efficiently without really need to, I don't really have to permute the arrays again. I can use the permutation that was done in the very beginning. Okay, so any questions? Can we? You're muted.
Yes, actually there is one question related to hierarchical ORAM. And the question is whether the extra lookups for dummies can help to guarantee constant time in implementations.
Sorry?
The question is if the extra lookups for dummies entries can help to guarantee the constant time of the implementation.
I don't understand the question. So the lookup dummies are necessary for security. So I don't want to reveal in which table I actually found the element. So I'm looking for the real element in each one of the levels. And after I found it, I continue to pretend to look up in the rest of the structure. Okay, so this is why I need the dummy lookup. Okay, so Panorama, two things they did. First, hash table of randomly shuffled inputs. And second, if you take randomly shuffled arrays, you can concatenate them and get a new randomly shuffled array. So in both constructions, they add an extra log n, which we have to shave to get the optimal construction. So Panorama, if this was Goldreich and Ostrovsky, non-recurrent hash table gives you an ORAM. Now we are saying you need non-recurrent hash table for shuffled inputs, something which is weaker, plus intersperse, this taking two randomly shuffled array and shuffle them together, this gives you the ORAM. Okay, so these are the building blocks that we have now. So let's take a look at intersperse. How does it work? So I have two arrays. Each one of them is randomly shuffled. Okay, so the first array has n0, is of size n1. Think for now they are both 4 elements for simplicity, and the size of the two arrays, the sum of the sizes is n. What I'm going to generate secretly, I'm going to generate an auxiliary array that has exactly n0 zeros and n1 ones. Okay, I can sample such an auxiliary array in the memory obliviously. I just like sample each one of the coordinates one by one. In the beginning, this one is going to be sampled. It's going to be 1 with probability n0, n1 over n, and 0 of probability n0 over n. After I chose, I adjust the probabilities and continue. Okay, so this is secret. Now, I'm going to oblivious route elements from the shuffled arrays according to this auxiliary array. So this auxiliary array tells me that I want here to have 0 from, I want an element from I0, and here it tells me that I want another element from I0, here it tells me I need an element from I1, and so on. Now I'm claiming that this will give you a randomly shuffled array of the entire concatenation of these two arrays. Why is that? So let's see how many possible outputs we have. How many possibilities we have for generating this auxiliary array? This is something like n0 choose n. Okay, we're going to choose n zeros out of n. It also says how many, where are the ones. Okay, so this is what this is the auxiliary array. And now we are saying this is randomly shuffled. So we need to shuffle now all the blue ones over here. And we also need, those are the possible shuffling of the second array. And overall, this gives us n factorial. So we get all possible outputs. Now, the idea is that we don't have to repay for the shuffling of each one of the arrays by itself. We just need to do this oblivious route. We have already, someone already shuffled it for us. We just now need to reroute the elements into the output array. So the challenge is to actually move those elements obliviously, and Panorama showed how to do it in n-log n. I'm now going to show you how to do it in order n, and the key building block is compaction. How this is going to work, so I'm going to take my two arrays, I'm going to generate this random auxiliary array, and then I'm going to run compaction on this auxiliary array. What I'm going to get, tight compaction, is I'm going to get all the zeros in the beginning and all the ones at the end. Our tight compaction was in the balls and beans model. It means that at the end of the day, it just moves balls around. It makes some calculations where to move the balls, which balls to move, but it does some computation. But at the end, it's just order n time and order n move balls operation. We can remember all the move balls that it did during the construction, during its lifetime. And then we're going to put our two arrays at the output and perform exactly the same move balls, but in the reverse direction. We are going to perform the same swaps in the reverse direction, and then we're going to get the output array as we want. Okay, so overall, this is order n, very easy given compaction. Questions?
No questions so far.
Okay, so what is now left is how to rebuild the hash table in linear time. We are now looking at a weaker primitive that suffices, and we assume that the inputs are randomly permuted. So again, we looked at Goldman-Ostrovsky, where we took all our elements. We saw how to do it, how to place the balls into the bins using oblivious sort. This cost n log n. It's too expensive. This log n become another log n. In the final construction, we want to shave this log n. Now, how do we going to shave it? I'm going to give you a guarantee that first, before we started, someone permuted all the elements for us. So the game is as follows. The adversary chooses all the elements that we have. It knows all the balls, okay? But before we start the construction, someone shuffled all the elements, and then we start the construction. Okay, so the adversary knows the balls, he chooses the input. Now someone, for free, shuffled all the inputs, and then we start. So the question is, what happens when X is randomly permuted? Can we just throw the balls into the bins? Okay, so it's randomly permuted. The adversary chose the input, someone permuted all the input, we don't charge for it. And then I'm asking, can I just throw the balls into the bins in the clear, where the adversary can see which ball resides in each one of the bins? Apparently, there's no problem with that, right? Like, it doesn't know which is this ball. I mean, it doesn't know that it might be this one before the permutation. It doesn't know which ball is where. And I can also simulate that. The simulator can take the build. The build procedure will be just take n balls and throw them randomly into bins, into n over log square n bins of size log square n each. Okay? But even though the build is simulatable, the entire construction is not secure. And why it's not secure? Because the lookups reveal information. So the adversary, it later can do lookups as it wishes. It chooses which elements it's going to look up. If it performs n relookups, the access pattern, or at least the loads that it's going to see, are going to be exactly the same as in the build process. And if it's going to perform a dummy lookup, it's going to be a new balls into bins distribution, new sampling of balls into bins into our bins. Okay, it's going to be completely independent of the build procedure. So we have here an algorithm that we can simulate the build, we can simulate the lookup, but we care about the joint distribution and not just each one of them independently. Okay, so what are we going to do? So the way we're going to build is as follows. We're going to take our n elements and throw them into the bins. Okay, so first we have the n elements. Someone randomly shuffle the elements for us. And then we're going to throw the elements into the bins according to the PRF key, as previously, while completely revealing the access pattern. Now, we are going to sample an independent secret loads of throwing less balls. It's going to be n minus n over log n into the same bins. But it's going to be secret. I'm not going to reveal it to the adversary. So I'm just going to sample a number, secret loads. Now I'm going to take this structure and make two copies. One copy, I'm going to copy secretly up to the threshold, the secret threshold on the left, and take all the real elements. And above the threshold, I'm going to continue with dummies. And on the right-hand side, I'm going exactly the opposite. I'm going to copy until the threshold with dummies, and then I'm going to write the reals. So just to say how to do it. So I'm going to take a bin. I'm going to scan the bin and write in two other bins at the same time. Until the threshold, I'm going to write on this one a real, on this one dummy. After the threshold, I'm going to write dummy over here and the real element over there. Okay, everything is secret. I still didn't reveal the secret loads. Now overall, the overflow pile, this I'm going to call it the overflow pile. These are the major bins. In the major bins, according to the secret load, I'm going to have n minus n over log n real balls. And here, overall, I have only n over log n real balls in this entire structure. So what I can do now, I can write tight compaction again on this one, remove all the dummies, and get an overflow pile which contains exactly n over log n elements. On this one, I can build now, I can build a structure, a hash table, using Oblivious source. On this one, on the other end, I have my major bits. Now the claim, how are we going to do a lookup? So to look up, we first are going to search in the overflow pile. If we're going to find the element, then we are going to visit a random bin. If we are not going to find the elements, they are going to visit according to the actual PRF key. Okay? The idea is here that we can actually do a hash table while paying a lot for building this hash table because it doesn't contain a lot of balls. And here in the major bins, we threw everything into the major bins in the clear without revealing, without doing Oblivious source. The question is, why is that secure? So let's take a look at the security argument. So in the build process, what we revealed the raw loads of the entire structure, right? On this entire balls into bins, of n balls into the bins. And then during lookup, we kind of, during the build, we removed some of the elements to the side. And during lookup, we moved some of the elements to the overflow pile. And whatever now real element that is found in the overflow pile, we're going to visit a random bin during lookup. So it's like throwing n minus n log n balls into the bins, and then the remaining n over log n balls, we're going to again throw into the bins independently using fresh randomness. Okay? So overall, it's like throwing n minus n log n real balls into the bins, and then the remaining n over log n again throwing into the bins. We're going to get a completely independent balls into bins loads independent of the build process. Okay, so these two are going to be two independent instances of balls into bins. Any questions?
No questions.
Okay. Okay, so this is the main trick, how we can actually build the hash table in linear time. The idea is that I'm taking all my balls, throw them in the clear. Some balls I'm going to put aside secretly, and then it's kind of hashing them again in the access pattern, while actually it's like obscuring the access pattern later. Okay, so now all is remaining is like showing how to actually search inside each one of the bins. I'm not going to show the entire construction, but we need another trick to actually do it. So we are working in the RAM model where the word size is W, and say that you have n balls, each of size d bits. How much, what is the cost of actually running an Oblivious sort on these balls? So if you have really, if your element doesn't reside in one block of the ORAM, you need like several balls. This is the cost of Oblivious sort. Okay, it's D over W times n log n. But what if D is much smaller than W? Particular, if one ball, if one RAM word can contain a lot of balls and not just one, or you don't need more than, it can contain many balls. So the idea is to use packing. We can put D over W over D balls in one memory word. And then we can sort in time, instead of having the ceiling, we can just remove the ceiling. In time, which is D over W and log square n. Let's say we are using Bytonic sort. And when n and D are small, okay, when n is something like a polylog n, W to the 4, and D is log W, we can sort in time which is linear and not n log n. Okay? So the idea is to do SIMD operation, like single instruction, multiple data, and we can sort, when we pack a lot of elements into one memory word, we can actually sort much more efficiently. Where are we going to use this packing trick? So each level in the ORAM is just a lot of bins. Each element resides in a random bin. The size of each bin is polylog n. And when we have polylog n, the metadata telling where each element is going to be log n. Okay, because if we have something which is just log polylog, then pointers is something like log. And so we can essentially compute on metadata, on pointers, and compute where to place each one of the balls in a packing way. And then, therefore, we can actually shave the log n that comes from this place using this packing trick. So I'm not going to get into the details on this one. I want to say also that this packing trick also comes, I described in the previous talk how to do the Oblivious tight compaction in the circuit model. I did not describe how to do it fully in the RAM model, but in the RAM model, we also need to use packing to actually achieve linearity. Okay, so for the last to conclude, I'm going to talk about how to move from amortized complexity to worst case complexity. So what we have, the construction that we had so far, we got a taste of this log n overhead construction in amortized sense. Some operations are longer, they require order n operations. Like if I need to build now the last level in the ORAM, then I need to intersperse all the levels up to that level, and then run the hash table. This is going to cost order n, it's going to introduce delays and so on. What I want to do, I want to have order log n overhead in worst case. So the problem is that classic deamortization technique of hierarchical ORAM, which goes back to Ostrovsky and Shuk from 97, it's not compatible with the construction of Panorama and Panorama. Let's see why. So before I even start, I would just want to mention that what I described is the rebuild process where I take all the levels and push them to the last level, or push like levels into many levels into one level. It's a bit not so friendly with the amortization. Instead, we can look about an alternative procedure which is more friendly, where I just push each level one level down. Okay, so I'm going to push all the elements over here to the next level. I'm going to get half full. This level is going to become half full. I'm going to push this level to the next level, and this level again is going to be half full. And this level was before the procedure half full. I'm going to push it down to the next level, and this one is now going to be full. Remember that this is of size, let's say n. This is of size 2n, but before the procedure, it is half full, so it contains an element. So after the procedure is going to contain 2n elements, and it's actually full. So what we have now is just like we can push down each one of the levels. How does it help us? So we have kind of two procedures. One is where we push down the levels, and one when we push the element and merge. This is when we come to the final one that we actually want to rebuild. We just push it down and merge the two levels. So we have two kind of procedures. One is just push down, compute. You kind of build a new level just from the content of the level above. And in this one, we're going to build it from our level and the level above. What is good about this procedure is very friendly for the amortization. It is slower rebuild, and therefore it's easier to deamortize. And moreover, we now don't need to look on the entire structure and pushing it into the last level. We just need to look at the level above, and that's it. Okay, so the deamortization is going to look at two consecutive levels, and that's it. So how do we deamortize? Now I'm going to look only at level I. So level I, its lifespan of each one of the level is, it's half full and then becomes full, and then we push it to the level below us. It's half full, and then it's full again, half full, full, and so on. Now, I'm now going to look only at level I. At level I, if this is the lifetime, I'm going to build level I already at this point. Okay, I'm going to start the rebuilding of level I already after this level was built. I know exactly what elements I want to rebuild level I from. Okay, so I can start rebuilding level I far in advance. So at this point, I already can start rebuilding level I. At this point, again, I can start rebuilding level I. I know far in advance before the deadline, I know to start to rebuild. I do this process on the background. Every access, I'm doing a little bit of this process. And so when we reach the deadline, when we actually need the new table, the table is already built and ready, and we can use it. What happens when we come to use this deamortization procedure? Okay, so this is the deamortization procedure with classical hierarchical ORAM. What happens when we come to use this deamortization with Panorama and Optorama? The problem is this randomness reuse technique that we mentioned. So in Optorama and Panorama, we have security as long as we never reconsume the randomness of that element. So we say, as long as you didn't visit that element, the adversary has no idea what resides in that element, and therefore it's still randomly permuted in the eye of the adversary. So if I want to start rebuilding my table far in advance, while still accommodating lookups in the level above me, it might be that this element, this randomness, is going to be consumed, and this is going to break security. Okay? So the deamortization techniques of Ostrovsky and Shub do not work with Panorama and Optorama, and the construction is just in amortized sense and not in worst case. So this is the main challenge, is that at this time, when we start rebuilding level I, maybe we're going to look up for 25, and this will mean that the entire security of our hash table is broken. So the main idea to solve this issue is to have 2 copies of each one of the levels. And each level has an active copy and a copy that is being rebuilt. And the idea is that if I'm going to do lookup over here, I'm going to rebuild the other copy. And when this one is being rebuilt, I'm going to use that lookup. So the idea is to have some cascading construction such that when this one is being rebuilt, if I'm going to look up over here, then the randomness over here is going to be reused, but not this one. And so we can adjust and have independent randomness between the 2 copies. It's a little bit, actually how to do it is not so easy, but the overall idea is again to have 2 copies, one I'm using, one I'm being rebuilt, and kind of balance between the 2, so that we never actually reconsume the randomness when we come to rebuild. So that's it. That's what I have. So for conclusions, we saw lower bound, how the lower bound cost of ORAMs are log n. Yesterday, we also saw the tree-based ORAMs of log square n. We also saw some oblivious sorts and some advances in sorting circuits. And now we got a flavor of the computational security and of Optorama and Panorama, where we can actually achieve log n in worst case. Some references, what I talked about in this talk, for whoever is interested, and that's it. Thank you.
Thank you. There is one question actually related to the implementation. The question is, the asymptotic results look very nice, but do they actually result into improvement in practice? In particular, do you have elements of comparison about the constant cost between the tree-based ORAMs state-of-the-art and the hierarchy-based ORAM state-of-the-art?
No, so the constants are really bad, especially if you want to shave this log n. We saw the previous talk how you can have very nice tight compaction in n log n, and we want to shave this log n. You pay extra factors in we use expanders and stuff that is really costly. I don't know exactly the comparison between the log n and log square n. It's still work in progress. But we do understand now that the theoretical, we know that the theoretical result, we know that the lower bound is tight, and we need to achieve this log n. This is what, this is where we need to push our efforts.
Okay, thank you. We don't have further questions.
Okay, thank you.
Okay, great. Thank you very much. That concludes the oral session and the 3 talks. We'll take 15 minutes break now, and we'll resume with the next session about vector order. Thank you very much.
Thank you.